Hello, this is Christine Halsey, and today we're going to look at how to use a BJT. BJTs, how does it work? Well, there's two ways that a BJT can work. It can work as a switch, where it saturates or fully conducts between the collector and the emitter, or it cut off and there's no conduction between the collector and emitter. This actually produces ones and zeros. It can also work as an amplifier. The base controls the current. The base current controls the amount of amplification. And when we apply current to the base, what happens is we allow the collector to flow to the emitter. This pretty much becomes a short and joins the collector and the emitter junction. When it's in cutoff, then the collector to emitter junction will have the complete amount of voltage there that's applied to the circuit here. So if all the voltage is here, this is acting like an open or a big resistor and consuming all the voltage. There's no voltage for the rest of the circuit. Okay. In a BJT, the currents combine. So the emitter current, which is the current through this branch, would be equal to the collector current plus our base current. We can then translate so that we could solve for either of those values. If we were solving for IC, for example, and we had 45 milliamps and 450 microamps, we need to watch those units or at least put them in the calculator correctly so that we make sure and do the conversion here and come up with the correct answer. Okay, in BJT we have what's called the beta. To me, this is the gain ratio, and it's given on the data sheets. Usually we can determine it approximately from IC over IB. And if we go using the previous example, the 44.55 milliamps that we saw for IC and 455 microamps that was given for IB, that gives us a beta of 99. Okay, if we look at figure 3-66, following example 3-1, we can calculate the base current, which will be the current directly applied to the base that determines whether this conducts or does not conduct, whether it acts as an open or it acts as a short, or in between. All right. So here we have VBB minus VB over RB, and these equations used to drive me crazy when I first started hearing them. All right. The more you practice, the more you get used to it. So we have 2 minus the 0.7 volt. There's a diode assumed here at 0.7 volts. And we divide that by the 4.7k ohm base resistor, because it's 276.6 microamps. Then to determine the collector current, we use the beta that's given times the base current to determine the amount of gain in that current. So the 277 microamps applied to the base is going to help us conduct 20.7 milliamps of current through the collector. IE, our emitter current, is IC plus IB. So we add those two together, making sure to convert to the same units or enter them properly in your calculator. For VC, we have VCC minus IC times RC. So we take our IC that we calculated above times the value given for the resistor. And we can determine here that the collector voltage is 15.1 volts. Okay, there's what's known as the DC load line for a BJT. Here we're looking at figure 367. And this is from the book as well. Whoops. It shows how to break it down and look at it as a Thevenin equivalent circuit and use that to determine the saturation and cutoff points. So IC sat, or the saturation current, when it's how much current when we're fully conducting will be going through the collector. And we use VCC over RC to determine that. 10 volts over 1K, that would be 10 milliamps. So when we saturate it or fully turn it on, we have 10 milliamps. Right? The VCE cutoff is equal to VCC, which in this case is 10 volts. The current at that point is 0 milliamps. Now, what that tells us is that, again, the point between the collector and the emitter measures 10 volts. That means this is consuming all the voltage and there's nothing left for the rest of the circuit. I'm sorry, in our example it was 24 volts. I do believe oh no, it is 10 volts. Okay, that was the last problem that was 24. Sorry. So we're looking at a cutoff point here. This is an open in the circuit. When it's in saturation, it's like a short and we're fully conducting. And when it's an open, there's no current flow because all the voltage is being consumed here. If you've never created an open and measured things and done a short and measured things, I would suggest trying to safely do that because it's really fun. I'm pretty sure there's some examples out there how to safely create an open and a short in a circuit and make the measurements. The best way to do it is in multisim because you can go into each component and create a fault and create either an open or a short and look at what, and then make the measurements and see what happens. All right. Here's it's following example 3-3, and we calculate the minimum current using VCC minus VBE divided by RC plus RB divided by our beta DC. All right, so for this example, that's 10 minus 0.7, and our 2.7K plus 680K divided by 300, which was the beta that was given. And that gives us 4.2 milliamps for our minimum collector current. The saturation current, VCC over RC, so 10 volts divided by 2.7K is 3.7 milliamps. VCE we can calculate as VCC minus our current times the resistance. 10 volts minus the 3.7 milliamps and 2.7 kiloohms gives us 9.9 volts. So then we have 10 minus 9.9, which is 0.1 volts for VCE. Okay, so if we're measuring 0.1 volts here, what are we seeing? And we're seeing a 9.9 here. Is this acting as an open or a short? Is it conducting? Is it saturated? And, oops, our last problem here with the voltage divider bias. Okay, I would keep these notes because once you learn to do this, this is repetitive and you just learn to plug in the right values in the right places. So to solve for the base voltage, we have R2 over R1 plus R2 times VCC. This is all based on the voltage divider rule and Ohm's law and everything you've learned so far. Yeah, the voltage divider rule, that was the one, Ohm's law. Two I was trying to think of. I think there's another one in there too. Oh, Kirchhoff's voltage law. So we have 6.8K divided by the combination of 6.8 and 56K. And then we multiply that times the 15 volts. So this gives us a ratio of this input voltage for the divider. And that gives us 1.62 volts. Minus 0.7 for 0.924 volts or 924 millivolts. All right. Then we can calculate our emitter current. We take that emitter voltage and we divide it by the emitter resistor, Ohm's law, easy peasy. So we got 0.924 volts divided by 1 kilo ohm, that gives us 924 microamps. IC is approximately equal to IE, so therefore IC is 924 microamps. VC can be found by taking the supply VCC minus IC times RC. This is a combination of Ohm's law and Kirchhoff's voltage law. So we have 15 volts minus the 924 microamps times our 6.2 kiloohms. So that gives us 9.27 volts across RC. I'm sorry, this gives us RC, this gives us VC, which is from the collector to ground. VCE is then determined from that 9.27 minus the 924 millivolts that we found for VE, and we have 8.346 volts from V collector to emitter. Thank you. I hope you enjoyed learning about BJTs today.